Buongiorno, mi fa tanto piacere di essere qui in Italia e volevo ringraziare la gente che ha organizzato questa conferenza, era stupenda, mi fa tanto piacere anche di essere in Italia perché mangiare in Italia è magnifico. What, are we supposed to do this in English? Oh shoot. Olivier, are you prepared to do this in English?
Sì,
Yes?
sì, grazie mille.
I loved it when Samantha did this yesterday. Am I supposed to speak in English? Okay. So we are asking the same question ourselves. So we'll start our presentation here, and I would like to start with something. Everybody's talking about water here, and everybody's talking about the inner solar system. I don't like the inner solar system. I don't even like the Earth. So Olivier and I are going to convince you that it is useful to take a trip, take a hike, and go to the outer solar system somehow. But before this, everybody's talking about water and habitable conditions, and this is what we're going to do also with this. But does everybody understand what habitable conditions are? Okay, so what do you need to live, to be alive? Maria Antonietta, what do you need? Ma che cose hai bisogno? What do you need? Cibo. Ah, yes. Okay, cibo. No. 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 Okay, so let's start with the basic thing. Everybody's been talking about water. Okay, in Italia, I would have hoped somebody would say something about vino. But okay, I mean, when I'm in France, they start wine. Okay, so fine, or birra. Okay, you need liquid. Okay, water. Then you need to eat. Okay, cibo. All right. And what else do you need? No. The primitive life didn't. So I'll take half of my time for the presentation to tell you that if I had put you in a freezing environment, you would not survive. So you need heat, energy. On Earth, we have the sun, but out there in the outer solar system, not so much. So what we're going to be looking at is an environment that has water, that has something to eat, the famous SNOPs, the organic molecules, and also can survive with some sort of energy, some sort of heat. It could be energy from tides, it could be energy, chemical energy, it can be all kinds of things. So this is what astrophysicists actually look for in the outer solar system. So when we discuss habitable conditions, please bear with us because we are not talking about life immediately. We're talking about looking and finding in the outer solar system places where there may be these conditions. And one of these places is obviously Ganymede. Ganymede, you all know, of course. Ganymede is the biggest satellite in the solar system. It has a lot of nice features. Not only it's the largest satellite in the solar system, we think, you see what, is this the pointer? Yes, what you see here in blue is what we will call a hydrosphere. A hydrosphere is liquid water ocean, and we think Ganymede has a magnitude, an order of magnitude more water than all the oceans on the Earth. And you've seen before from the previous presentations how tiny actually the water that we have in our oceans and how precious it is to preserve it. So it's very important to see that Ganymede has all of these features, and it also has another unique feature, which is the internal dynamo and an induced magnetic field. This is unique for a satellite in the outer solar system. And it has also a very cratered surface all around it, similar to actually what we find on Callisto. Callisto, we also have a testimony of very ancient ages with the craters that we have on the surface here. But we don't know a lot about Callisto, except that my daughter is called Callista, and it means the most beautiful. I don't know why this satellite is the most beautiful, but we were honest parents, so we called them like that. And it's also a mystery in terms of whether there is a hydrosphere inside, but what is the kind of differentiation you have inside the satellite. But in any event, studying Callisto will tell you a lot about ancient times in the outer solar system from the craters, but we know it's not active, contrary to Europa. Europa is a fabulous satellite. You'll hear more about it also when we discuss the Europa Clipper mission. But it's important to note that we know a lot about Europa, and in particular the fact that we think from the morphology that we have seen from the famous Galileo mission that was there until 2003 in the 90s, that Europa has probably a liquid water ocean that is very important and unique because it's close to the surface on the one hand. And on the other hand, it's probably maybe in touch also with the core of the satellite, which is very important because, as Jean-Pierre explained to you, the fact that you have this contact between the core of the planet and the rock and the water ocean, on Earth at least, is very favorable to life. So on Europa, we may have an active world, and we may have the best example of a liquid environment here in contact with the silicates and also very close to the surface through these regions that we call active chaotic regions. And so this is the reason why we want to go to this place out in the Jupiter system. And you heard about the Juno mission, a wonderful Juno mission, but we are going to do a little bit more different things, and that is to look first at Ganymede, this satellite here, that, as I said before, has an induced magnetic field. And what this means is that the interaction with the Jovian magnetosphere is coming through, producing this induced magnetic field, means that there is a conducting layer under the surface. And this conducting layer is an indirect indication of the presence of this liquid water ocean. We think that's how we detect it, and in different other ways. But also it has this internally driven dipole magnetic field and an interaction of the mini magnetosphere with Jupiter. So this is a very, very complex system. The only way to disentangle the different components here is by sending a mission on location. And looking also at the auroras that have been detected by the Hubble Space Telescope on Ganymede, we find that their tilts are not as the variations of the tilts are not as strong as they should have been, indicating also that there is this layer, this conductive layer under the surface that means that there is probably water. The question about Ganymede is, can we have a transport from what we find on the surface inside the liquid water ocean, and can this ocean now become habitable if you don't have all the conditions that we mentioned before? But for all these reasons, we wanted to go, and ESA decided that we would have its first large mission in the Cosmic Vision program 2015-2025 to go to Jupiter. And I was there from the beginning, from the inception of this mission that was at the time called Laplace, and it was Michel Blanc who started this project. And it was a wonderful time because at the time we were going to go together with NASA to the Jupiter system and do both Europa and Ganymede. And it's something that is actually going to happen in the future because at some point the two spacecraft are going to find themselves together in the Jupiter system and do some synergistic science. That will be wonderful. But again, what we have here is a great mission that I was happy to attend in Guyana, in Kourou, in Toucan. And so I cannot exactly impersonate Patrick Michel, but I can go, yes, go Juice, because that is exactly what we did on the spot. When you have a launch, and this is the best thing that I can wish for the young people here, when you have a launch, you're there, you go Juice. That was a month ago, and my voice is still Marlene Dietrich, that many of you don't know, but it's my morning voice because I've been screaming so loud since that time, like Patrick did, because a launch is a wonderful thing. So we launched this mission on the 14th of April, and one of the major elements of this mission, one of the major assets, is that it is going to be actually the first spacecraft that is going to go into orbit around a satellite. Okay, we haven't done this before, and Europa Clipper is going to do flybys, but this is going to be the first time, and it's extremely important to go into orbit around an object that you really want to study in depth. So we're going to go there with all the instruments. You see here the launch. You see the happy faces. I'm here with all the PIs of the instruments. We're all going, eee, we made it. And here is Olivier with the other group at ESOC. You can see all happy faces because all of these people have worked for 13 years to get this mission en route. And this mission here has all the instruments that you see here. There is a remote sensing suite with spectrometers of different kinds. And the camera, I'm a COI on the Janus camera here. You have geophysical experiments that you see here with all these different instruments, including RIME that Wlodek just mentioned before, and a suite of particles and fields investigations. And all of these instruments coming together will tell us a lot of things, but I just want to mention that it's not the fact that you have the individual instruments in a mission. It's the fact that you can combine the measurements from the individual instruments. And for instance, if you combine all the instruments that you see here, the fields and particles, the imaging and the sounders and radio science, you can do a lot of things to study what is the ocean, the ocean depth, the ocean, the crust, also thickness on Ganymede and on Europa. And that comes by studying the eccentric orbit of the satellites that leads to surface deformations and the periodic variations in the rotation. It's what we call the librations. This will actually give you here the icy crust here, the icy crust depth. And on the other hand, if you do the magnetic induction from the field vector, you can get actually the depth of this ocean. So you can see from remote sensing, not going there, not digging inside, you can look at these two things. So we will do that, and we will also study different things in the system, including Jupiter, the giant planet, in the sense that Jupiter is being studied currently by Juno, but we will do some complementary observations here and look at coupling processes and the Laplace resonance among the three satellites, Io, Europa, and Ganymede. And all of this is very, very important because these bodies here that have this liquid water inside, whether in contact with the silicates, whether close to the surface to see the organics that actually Jean-Pierre was mentioning before, can go into the ocean and create the habitable conditions with the tides and with the tectonics on all of these bodies, make these icy moons actually a very, very strong case for archetypes of exoplanets in the solar system and beyond. So this is the importance of the objectives that we have for the JUICE mission. And now Olivier will tell you more about the mission itself.
Okay, thank you, Athena. So just quickly, how the spacecraft will look like. Athena already discussed a little bit the payload. So we have a huge spacecraft with huge solar panels because we are far from the sun. All the optical payload, they are on the special optical bench for optical stability. We have a long radar boom to make precise measurement of the magnetic field, which was successfully deployed. We have a radar antenna that Wlodek was mentioning that in his talk. Unfortunately, it's still not deployed. This is the main issue on JUICE at the moment. You may have heard about it. Over the last 2 weeks, we tried to solve the problem. There is probably a pin which prevents the antenna to be fully deployed. And in the last 2 weeks, there have been a lot of thermal cycling of the spacecraft to hit the brackets and to try to shake the spacecraft as much as possible. And today, we'll try to release, to activate an actuator to hopefully release the antenna. So let's see what happens, and we need to have the finger crossed, hopefully, fortunately. That was the launch on the 14th of April, a very emotional moment, very intense. It was quite stressful because we have a 20-day launch window, but every day there was only 1 second to launch because of the special parameters of the trajectory. And the first day there was a delay due to lightning, so because it was a 1 second launch window, we had to postpone to the next day. But fortunately, we managed to launch on the 14th. The trajectory from Ariane from the Ariane launcher was just perfect. So we saved some propellant for future operation. And because of the timing of the JUICE project, we launched in the middle of the launch window, which is also very good in terms of propellant. So we have reasonable margin in terms of fuel, we can dream of an extended mission to go even in lower orbit at Ganymede. So that was the selfies sent shortly after separation. That's the timeline of the mission. So launch 1 month ago, and the impact on Ganymede at the end of the mission will be in 2035. Given the schedule of the mission, we are in the middle of the project. If you consider the mission started in 2007 with the call of proposal, and the end of the mission archiving 2036, 2037. So we are just in the middle of the project. And many people are asking me, now that you have launched, you have nothing anymore to do, you can hibernate, you can find another project. No, because we have to work to be ready when we arrive in July 2031. We have 4 years of mission, and I think we really need these 8 years of cruise phase to fully prepare these 4 years of mission, which include flybys of Europa, Callisto, Ganymede, the Ganymede orbit insertions. There will be a lot of work to do to prepare this phase and to be fully ready on time. That's how the trajectory looks like. Michael Kahn yesterday explained how we reached Jupiter in 8 years due to the capability of the launcher, due to the heavy mass of JUICE, so we need 4 gravity assist flyby. I would like just to mention a very interesting one in August 24. It will not be only a Earth gravity assist flyby, but a lunar Earth gravity assist flyby. First time we do that, should be quite spectacular. Here just some examples of, this one. Just 3 moments of the JUICE trajectory. So this one is just before going into orbit insertion into Jupiter, we do a flyby of Ganymede to decelerate the spacecraft. So we use the gravity assist not to accelerate, but to decelerate and to help the Jupiter orbit insertion. That's also an interesting navigation moment. Then there will be the Europa flyby, very intense phase of the mission because we have only 2 flybys, so at 400 kilometers. So for doing these 2 flybys, we'll operate all the instruments together to learn as much as possible about Europa, and it will take 2 to 3 months to download all the data on the Earth because we will require a lot of data during those 2 flybys. And finally, the last phase of the mission, once the mission will not work anymore, either the spacecraft will not work or there will be no propellant on board, will for sure crash on Ganymede. And maybe there will be Europa Clipper that will witness this event. We will see later how it does that work. Talking about Clipper, Athena mentioned that we will be quite lucky to have at the same time 2 spacecraft in the Jupiter system, and that's an animation of what can happen in 2032. So you have the 2 spacecraft here, Clipper and JUICE, heading towards Europa in this particular sequence. So there will be a lot of opportunities to do synergetic science, work together with the 2 science teams. We are very excited by that for Europa science, but moon science, plasma science, it will be very interesting. So I think I will stop here. Go JUICE. Let's cross the fingers for the radar antenna. And maybe in 10 years from now, to the students, you will be working with us on the data. So I'm welcoming you already. Thank you very much.